Hi viewers, this is Shankar, and in this video we are going to discuss about the evaluation order for syntax character definitions. Let's go to the video. In this topic, evaluation order for syntax character definitions, we are going to discuss about what is a dependency graph and what are the ordering of evaluation of attributes and what is S attributed definition, what is L attributed definition, and finally semantic rules with control side effects. Let's see the first topic, that is what is dependency graph. Dependency graph are useful tool for determining an evaluation order for the attribute instances in a given parse tree. A dependency graph depicts the flow of information among the attribute instances in a particular parse tree. An edge from one attribute instance to another means that the value of the first is needed to compute the second. So just consider the production and root. The production is E derives E plus D, and its equivalent semantic rule is E dot val equal to E dot val plus T dot val. So here at every node n labeled E with children corresponding to the body of this production synthesized attribute called val. And n is computed using the values of val at two children's, it's E plus T. We just consider the dependency graph for the given production. So here E derives E plus T. So this is the parse tree. The dotted lines are the parse tree. And here the attributes called val is a dependency graph for the its equivalent attributes. So as a portion of the dependency graph for every parse tree in which production is look like this figures. As a convention, we shall show the parse tree edges dotted lines, and while the edges of dependency graphs are solid. Next, it's an example of a complete dependency graph, and it's a dependency graph for the annotated parse tree called 3 star 5. The nodes of the dependency graph represented by the numbers from 1 to 9, and its correspond attributes in annotated parse tree is given in the figure. So here the nodes 1 and 2 represents the attribute lexval associated with the two leaves labeled digits. And node 3 and node 4 represents the attribute val, that is value, associated with the two nodes labeled f here. And next the edges 3 from 1, 3 from 1 and node 4 from 2 results from the semantic rules that defines f dot val in terms of digit dot lex val. In fact, f dot val equals digit dot lex val, but edges represents dependence, not equality. Node 5 and node 6 represents the inherited attribute t dash associated with each of the occurrence of non-terminal p dash. And next, the node h5 from 3 is due to the rule t dot inherited is equal to f dot val, which defines t dot inherited at the right side of the root from f dot val at the left side. And next, we see edges 6 to we see the edges to 6 from node 5, 6 node from 5, t dot inherited, and from node 4 for f dot val, because these values are multiplied to evaluate the attribute the inheritance node to the 6. The node 7 and 8 represents the synthesized attribute called SYN associated with the occurrences of T dash. Next, the edge to node 7 from 6, node 7 from 6 is due to the semantic rule T dash dot synthesis is equal to T dash dot inherited associated with the production. And the edges 8 from 7, and just 8 from 7 is due to semantic rule associated with the production 2. And next, finally, the node 9 represents the attribute t dot val. So the edges to 9 from 8 is due to the semantic rule t dot val equal to t dash dot synthesis attribute associated with the productions. Next subtopic is ordering the evaluation of attributes. The dependency graph characterizes the possible orders in which we can evaluate the attributes at the various nodes of parse tree. If the dependency graph has an edge from node m to n, then the attribute corresponding to m must be evaluated before the attribute of n. Thus, the only allowable order of evaluations are those sequence of nodes n1, n2 up to nk, such that if there is an edge of the dependency graph from ni to nj, then I must be less than j. Such an ordering embeds a directed graph into linear order and is called a topological sort of the graph. There are other topological sorts as well as 1, 3, 5, 2, 4, 6, 7, 8, 9. If there is any cycle in the graph, then there are no topological sorts. That is, there is no way to evaluate the SDD on this parse tree. If there are no cycles, however, then there is always at least one topological source. To see why, since there are no cycles, we can surely find a node with no edges entering. If there were no such nodes, we could proceed from predecessor to predecessor until we came back to some node we had already seen yielding a cycle. Make this node the first in the topological order, remove it from the dependency graph, and repeat the process on the remaining nodes. The given graph, already we have one order that is called 1, 2, 3, 4, 5, 6, 7, 8, 9, and there are other topological sorts as well as the 1, 3, 5, and 2, 4, 6, and 7, 8, 9. It is the another one. The next one is attributed definition. So as mentioned earlier, given an SDD, it is very hard to tell whether there exists any parse tree whose dependency graph have cycles. In practice, translations can be implemented using classes of SDDs that guarantee an evaluation order since they do not permit dependency graph with cycles. Moreover, two classes introduced in this section can be implemented efficiently in connection with top-down or bottom-up parsing. An SDD is STD is attribute if every attribute is synthesized. So the STD of figure is an example of S attributed definition is given below. Each attribute called L dot val, E dot val, T dot val, and F dot val is synthesized. So there are 7 production is given. First production is L derives En. For this equivalent semantic rule for synthesized attribute L dot val equal to E dot val. Second production E derives E1 plus T. So its equivalent semantic rule is E dot val equal to E1 dot val plus T dot val. And third production is E derives T. Its equivalent semantic rule is E dot val equal to T dot val. Next, fourth production T derives T star F. Its equivalent semantic rule is T dot val equal to T1 dot val into F dot val. The next fifth production T derives F. Its equivalent semantic rule is T dot val equal to F dot val. Next, sixth production F derives expression. Its equivalent semantic rule is F dot val equal to E dot val. And the last production F derives digits. Its equivalent semantic rule is F dot val equal to digit dot lex val. The next one is L attributed definition. The second class of SDDs is called L attributed definitions. The idea behind this class is that between the attributes associated with the production body, dependency graph edges can go from left to right, but not from right to left. More precisely, each attribute must either synthesized attribute or inherited attribute. In this case, you just consider the semantic rule for the inherited attributes, which are repeated here for the convenience. The productions are f derives ft dash, and T dash derives F T1 dash. So its equivalent semantic rule for T derives F T dash is T dash dot inherited equal to F dot val, and T1 dash dot inherited equal to T dash dot inherited into F dot val. So the first of these rules defines the inherited attribute T dash dot inherited using only F dot val, and F appears to the left of T dash in this production body as required. And the second rule defines T1 dash dot inherited using the inherited attribute T dash dot inherited associated with the head, and F dot val, where F appears to the left of T1 dash in the production body. And the next subtopic is semantic rules with the controlled side effects. In practice, translation involves side effects. A disk calculator might print a result. A code generator might enter the type of an identifier into symbol table. With SDDs, we strike a balance between attribute grammars and translation schemes. Attribute grammars have no side effects and allow any evaluation order consistent with the dependency graph. We shall control the side effects in SDDs in one of the following way. Permit identical side effect that do not constrain attribute evaluation. In other words, permit side effects when attribute evaluation based on any topological sort of the dependency graph produces correct translation where correct depends on the application. Constraints the allowable evaluation orders so that the same translation is produced for any allowable order. The constraints can be thought of as implicit edges added to the dependency graph. As an example of an identical side effect, let us modify the disk calculator example to print a result. Instead of rule L dot val equal to E dot val, which saves the results in synthesized attribute L dot val, which is consider the production L derives En. Instead of L dot val equal to E dot val, here just we write the semantic rule as print of E dot val. Here we instead of copying data from eval to L dot val, just we are printing the result. So here we are restricting that to store the memory location somewhere for copying the instructions. Instead of copying, just we are printing the values. Thank you all for watching this lecture series.